One important consideration in naming plutonic rocks and intrusive features, and also in understanding how what's going on underneath the ground relates to what we're seeing on the surface, is this idea of the geometry of the pluton. So we talked about one type of geometry of plutons, and that's a massive pluton. If we have a massive pluton underneath the ground, we call that feature a batholith. Of course, we can't see it when it's underneath the ground, but these batholiths tend to get eroded down to over time. And then what we're seeing after the erosion is a giant mountain range like the Sierra Nevada mountains of California. But let's talk about two other types of geometries we can have. Both of them include the word tabular, and tabular just means like a tabletop. So something that's kind of flat and continuous like that. You can think of a board or a tabletop or a book or something like that. Those would all be considered tabular. And then the other word there, concordant and discordant. Concordant means it goes with the pattern around it, and discordant means it cuts across the pattern around it. So one of those we call sills and one we call dikes. Here's an example showing both those things. So here's an intrusive igneous feature shown in this reddish brown, and it's being intruded into layers, or was intruded into layers of sedimentary rocks. These almost horizontal layers here by the side of the road are sedimentary rocks. Some of them cut directly across the layers of sedimentary rocks. That would be called discordant. And if something is tabular and discordant, then we call that geographic feature a dike, D-I-K-E. If something, however, is tabular and concordant, if it follows the same pattern as the sedimentary rocks above and below it, then we call that a sill. So one way to remember that is like a window sill, right? That would be like running along the bottom of a window. In this case, it's simple to see because they're horizontal layers of rocks, and the dikes are, and the dike in this case is almost perpendicular up and down to that. But you can have different geometries. The dikes can come in at an angle, as is shown over here. In this case, the sill is still following the pattern of the sedimentary rocks shown in white and gray in the background. But sometimes the sedimentary rocks could be tilted. In that case, the sill here, it's still following the sedimentary rocks, even though it's no longer horizontal. And once again, the dike is cutting across those layers of sedimentary rocks. Here's once again an image showing underneath the ground where we have this giant intrusive igneous rock, part of a batholith here, and then there's all these cracks running up through the layers of sedimentary rocks that have been filled in first with magma that is then cooled into an igneous intrusive rock. And in this case, all of the ones that cut across layers, this one, this one, this one, this one, this one, all of these would be considered dikes. Some of them reach the surface, and they tend to leave these long linear high areas that are not very wide like a mountain. They're just narrow, but they're continuous over certain distances. And the sills, we would almost have to have something like a cliffside in order to see those, because they just kind of run along the layers of sedimentary rocks in this case here. But let's start with the dikes. This is an example here. This is a map that's made from changes in elevation, and it's in northeastern New Mexico, and it's showing all of these dikes here. As we can see, all of these dikes look like just almost like linear scratches through this. They're high areas, and they're indicating these high areas are very long and continuous and kind of parallel to each other, right? We're seeing them up here, we're seeing them down here, and some of those extending for miles and miles. Those would be superficial features that we could see that indicates there's some sort of dike underneath the ground there that is an igneous intrusive feature. For sills are not as common because once again, they tend to stay underneath the ground, but we can see in this case, the rock layers are tilted. And in this case, eventually this sill here, which is shown in like brown and green, comes to the surface and actually forms a cliff along this river here, which is the Hudson River in right outside of Manhattan. So if you were in the Bronx or the upper West Side, you would be able to see this intrusive sill on the other side of the river. And this is a famous sill. It's called the Palisades Sill because it's in the Palisades area of New York along the Hudson River. And we can see that the sill is once again here. And we can also see that they've kind of added these squiggly lines on this side and this side to show where what they call the baked zone is, but we would call that the area of contact metamorphism. So the contact metamorphism is occurring above and below the sill because this liquid magma squeezed in between these rock layers. It cooked the rock layers on either side, and then it solidified into an intrusive igneous rock. And this is just a picture looking across from the Bronx at the Palisades Sill, very big and continuous. It's a solid igneous rock here that is the thing that actually forms the cliffs in this area.